now it's on. Oy, yes, there we are. Can the people on Teams hear me? Whoever is on Teams? I take that as a yes. Good. Thank you all for coming on a Monday morning at 10 a.m. I'm impressed. My Monday morning 10 a.m. lectures at university were usually a bit emptier than this. I really appreciate you all for being here. Very happy to be here. It's my first time in Bengaluru, and I'm very impressed, and I really like it here. Also really like the southern food, so I'm very happy to be here. Yes, I'm here to talk a bit about what we're doing at REOR 20. I'll try to keep the salesy part low, and I'll keep the more use casey and academic part a bit higher to make it interesting for you. We're dealing with floods. Most of you dealing with floods or water in some way as well. More specifically, we're dealing largely with this problem, which is the big difference between weather alerts and flood alerts. Because we are aware, right, weather alerts are getting better. At least that's what I see, not just in Switzerland, but actually globally. But flash flood alerts and flood alerts, they are a bit behind, right? So even though you might have a very good rainfall alert, usually a flash flood alert looks something like this. Even though I've been just told that Bangalore has one of the first fully integrated flood warning systems operational. So here it might be a bit better, but largely in the world, this is a US example, you get a massive polygon that just tells you here it's going to rain a lot, and you have no clue what that actually means, right? It's not particularly helpful for actual actionable insights, neither for you as a citizen that maybe has a car out, or as a government or as a business that wants to protect its assets. There is a very clear problem for that, and since I'm speaking to a room full of water engineers, you probably know this. It's computational fluid dynamics. That's a solution and a problem. The solution is that it's extremely accurate in calculating how water flows. The most accurate thing we have, and it's actually pretty much perfect as far as lab comparisons are concerned. But in operational setups, this is a bit of a bottleneck, right? In operational setups, it's actually very complex to set up. I mean, I was told it took 10, 14 years to have an operational setup here in Bangalore, and that's actually good. That's fast, right? But then also to calculate accurate flood inundation is very slow and or very expensive, and usually actually both, right? So you pay for a high-performance computer, you let it run for a very long time, and then you have a more or less good result. Well, in an operational context, that's too slow, right? That's just too slow. If you want really accurate, fast warning, you need something that's at least fast, and if you want to have it global, you also need it at a lower price point. Otherwise, it's just not feasible. That's more or less the challenge we've set out to solve about 6 years ago. And on a high level, what we did is we basically trained an AI to learn fluid dynamics. That's now the businessy part. I'm going to tell you a bit more detail after. What I actually mean is this. So what we've done is we first built our own numerical solver, something similar to HackRAS, but we have full control over the source code. And then we started generating patches. That's what you see here, terabytes of patches of meaningfully representative flow situations, right? And we did this for all kinds of terrains. So from very hilly terrains to largely, I mean, for Switzerland, for example, alpine terrains, but also very flat terrains. And we did it for no rain, low rain, medium rain, and very high rain situations. So to really cover a large swath of different flow situations. Then the same, of course, with riverine, different riverine forcings, different river stages, and coastal stages. And the purpose of having such a large sample of fully controlled training data was then to make sure that the AI can generalize and abstract flow dynamics to be used anywhere on the planet. That's really the goal. What we have as an output then is a model that works really like any other 2D hydrodynamic solver. So it takes the same kinds of inputs, right? So digital elevation data and land cover at a very minimum. You can put buildings on top. You can, of course, then have soil saturation, drainage, and so on, but that's then for calibrated models. And then you put on top dynamic forcings, right? So rainfall, river forcings, coastal forcings, and then you let the simulation run. Now, I told you in the beginning, it's about cost effectiveness and about speed. What do we mean by that? Well, let me give you a benchmark. This is now a benchmark that we did 2 years ago. It's a bit of a, I call it a lab benchmark, where we took, for us, a fairly small area. This is in Switzerland, Burgdorf, 100 square kilometers at a 10-meter resolution, where we let it rain. We let it rain the 100-year event, which in this case is 74 millimeters over 6 hours. And if you look at the results from a numerical simulation, that took us 62 CPU hours to calculate. Okay, we paid for 62 CPUs, so it maybe took us an hour to actually calculate, but we had to pay for 62 CPUs to run that. And as you know, if you want to do more simulations or larger, that explodes exponentially in how many CPUs you actually need. And then we ran the same thing through our model. Important to say, our model has never seen this topography or this event. So this was a new sample for our model that it was not trained on. And our model needed 4 seconds on 1 GPU to practically produce more or less the same output. Now, you of course know when we talk about AI, it's never exactly the same. It's an AI, it infers, it's a statistical approximation, but in our tests, usually we use the Nash-Sutcliffe efficiency. It's a bit like a correlation coefficient, right? That we apply on every flooded pixel. So we don't just apply it at a river gauge location, we apply it on every flooded pixel in this area. And we generally, over time, achieve about an 80% NSE on average for our catchments, which, to be honest, for most global situations means that input data uncertainty is much bigger than modeling uncertainty in this case. So, okay, took us about 4 or 5 years to build a very, very fast flood model. And now what, right? We're a company, we're not a research institute. So for us, it's that important to actually make a business out of this. What can you do with that? Well, the first application we talked about in the beginning, it's the warning piece, right? And I'm going to show you an example pretty soon. But okay, how can we very quickly warn? How can we forecast flood events? That's clearly one application. With the warning, you kind of at the same time have a response, right? So, okay, a flood has happened. Where do I need to go and send help? Where do I need to actually go and send specific people? But then, of course, there's also a resilience aspect. And in the very end of my talk, I'm hopefully have some time to talk about that, because you're used to building risk models, right? And you might set up your model, you might click run and then wait for a few hours or a few days for a result to come around. But there's some very interesting applications that this kind of speed and scale allows us to do. But let's first talk about forecasts. We're already live with this over all of Australia. And now you might also be able to get a bit of sense of the scale of this. 100 square kilometers was a lab case. The real case is when it's actually live in a big country. And I mean, me being from Switzerland, I emphasize big country because being live in Switzerland is not that much of an achievement. Being live in Australia is. And here we have a little example, Hurricane Alfred, that hit last March, so just about a year ago. Very tricky to forecast from a precipitation point of view, but basically always at the sort of every 24 hours, more or less, we got a decent forecast for the next 24 hours. So that's how we applied the model to calculate what's going to happen in the next 24 hours given this rainfall forecast. Model setup here, very, very simple. Really just the topography and the land cover as a static data set, and then precipitation as a dynamic data set. We did, in this case, not even assume anything on soil saturation because it has been raining for a while already, so we just assumed 100%. Of course, that could be put in as well. And then we let the model run. And the way it then looks is that basically every 24 hours we get the forecast, the model runs for less than 3 minutes. In this case, so the whole area over Brisbane was, I don't know, I think about 10,000 square kilometers or something like that. And as a result, you get what you see on the right here, really street level impact at 10 meters resolution over the whole urban area. You also get it, let's see, does this actually move? It should. Yes, you also get an animation, of course, so you don't just know where it's going to hit, but also when it's going to hit, which is, of course, paramount if you want to do response effort, right? You need to know how long you have. In this case, mostly about putting your cars away, because even just putting it one side street over might have saved your car from drowning, right? Good to know. And okay, I could also show you some validation pictures, but for now, I'm going to go to the next example because it's probably even a bit more interesting for you. This was sort of our bread and butter, let's say, hurricanes. Hurricanes, they tend to be not that hard to forecast. Where it gets really, really tricky is in sudden, severe convective storms. So when you have very, very, very heavy sudden precipitation events that you might only have half an hour or an hour to forecast properly. That happened in Texas in July last year. I'm assuming you read about that. That was highly published, also in Swiss media, for example, was a children's camp that was swept away, sadly. That was such a severe convective storm cell. So it was known that it's going to rain heavily in the general area, but it was very, very difficult to predict where exactly. And we looked at this event with several forecasting models. Most of the forecasting models did not get the rain properly forecast where it actually fell. We've also worked with one or two commercial companies that did forecast. They were a bit better. But then we also ran it ultimately with the measured data, so the radar observations from the ground, to recreate what happened. Model setup, they're exactly the same, so no surprise. Topography from the USGS topo, very, very nice topography data set. Land cover and precipitation. Same story here. The model has never seen US data. Actually, that was the very first US case we have run ever last July. Took us about 2 hours to just find the right data, and then another half hour to get the data into the model. So 2.5 hours from zero to having the model set up. And then another 2 minutes or so to run, in this case now, an area of 1,500 square kilometers at 10 meters. Full hydraulics, right? Which, if you want to try this in HECRAS, depending on your infrastructure, might just not be possible. And this was a matter of less than 3 hours of total work, end to end, to have a simulation. If I can replay this quickly, but if you look very carefully, the rainfall started mostly here in the southwest of the catchment. And you also see, if I restart this, the rivers really mostly filling up first from the south and then washing down this catchment. This camp location was somewhere around here where two rivers are coming together. And also zoom in here a bit. You basically had the tents here and up here. These were a bit safer. And then you had a dining hall here as well. They were aware that they were at risk. So they did get a warning saying the rivers are going to rise. But it's again this question, well, what does it mean, right? River's going to rise. What does that mean for me? So you really need a full inundation mapping to really show people how at risk they are. Here we also found the river gauge, which is very nice. So in black, you see the measurement of the river gauge that was measured here. And in blue, you see what our forecast predicted. And I want to stress here again, right? This was a fully uncalibrated model, right? This was really just 2 hours of finding data, pushing all that data in and running it once, which, for us was a really good confirmation that as far as the fluid dynamics is concerned, so we go back to our lab case, our favorite lab case, is Burgdorf in Switzerland. And let's look at this from a risk modeling point of view, right? So for example, Burgdorf might want to know, well, where do I invest for resilience, right? It's a typical risk model application. Well, where should I invest to protect my people, my property better? Now, when you build a risk model, you usually look at return periods, right? What's the 100-year return period for a specific catchment, or 200-year? Also, I have an insurance background before that, so that was the same thing. Let's look at the return periods. So for a return period, you need a design storm where you say, okay, statistically, I derive a certain notion of a return period, a certain amount of water that falls once in 100 years, or actually with a 1% probability every year. For this catchment, this 100-year return period, as mentioned before, is 74 millimeters. However, the return period is a statistical notion. Now, you all know statistics. Statistics is never one precise number. Statistics is always a distribution. The weather services of Switzerland thankfully also give these nice curves where you see actually the 100-year return period with a 95% confidence is somewhere between this upper bound here. And if you look in here, that's quite a lot more water than if you go to the lower bound, for example, which is here, right? So a return period is not one value. But as a modeler, you usually have to reduce it to one value because of the computational bottleneck, right? But the question is, well, how do you choose exactly which return period is representative for your catchment? And even worse, this return period is derived from 100 years of data. But are the last 100 years representative of the next 20? Probably not, right? So your uncertainty actually increases even more thanks to climate change. So which value do you choose, right? And this is now really the beauty of having almost no more computational cost associated with actually running the calculation. You don't have to choose anymore. You just run the whole distribution, right? And with that, you can then actually start to really quantify the uncertainty around your notion of return period. Or, of course, the uncertainty around input data that you might have, right? What if you don't know the land cover or the absorption or the drainage capability of a certain area, right? Suddenly it becomes very cheap to run a lot of different simulations. And that really allows you, in particular, I think as academics and as scientists, really allows you to explore a completely new way of how to deal with risk, right? And this is really, for me as well, one of the really exciting things about this application, that it really allows you to open up the scope, and even with not so great input data, but let's face it, that's in the end always going to be an issue, right? We're always going to lack precise input data, no matter where in the world we are, to overcome this somewhat with these kinds of tools. With this, I think I'm going to stop for now already. I'm going to ask if there's any questions, because I would really love to also, have this a bit of an interactive session. But thank you very much for your attention. And yeah, looking forward to some very hard questions, hopefully. Thank you. Please. Us, right? But of course, what you can start doing, I mean, that's one of the other issues that we often see, and this is now really my insurance background, right? Traditionally, you choose one return period and you let it rain basically spatially homogeneous over the whole catchment with that one return period. For a tiny catchment, okay, that might be kind of an all right approach. For a large catchment, that's not an okay approach, right? The rain never falls spatially homogeneous. So of course, then you can try, for example, to generate your own small-scale scenarios. I mean, there's tools for that, there's applications for that. Of course, we as a company, we're never going to know where exactly rain is going to fall. But if you want to do it as a risk model, you can, of course, instead of running one return period with one rainfall over the whole catchment, you can basically start moving around rainfall cells, right? That's the easiest approach. We're also working a lot with historical weather data that we transplant slightly, right? So we start to vary it to still have proper rainfall cells, but have them happen in different areas of the catchment to exactly model this uncertainty.
There are questions where you tried out the different emission scenarios because you're modeling risks in the future. That's something.
Yeah, so that's something that we're working together with. Usually there's a lot of companies in the climate risk space. Actually, also in India, we have some meetings tomorrow with some very interesting companies here in Bangalore. I'm really looking forward to that. Usually already have some data around emission scenarios and what that might mean for extreme precipitation events. The very nice thing is, since it's so cheap and we basically have an API where they can connect to, if you know that, okay, you know, in 2050, my 100-year event is probably going to be 150 millimeters plus minus some uncertainty, you can just run this through the API and basically get the results. Actually, I can thank you for that segue. I can quickly show you this even since we have time. I do want to, let's see if this works. I think on Teams I'm sharing, so that should work. So if I still have internet, yes, it looks good. So as mentioned, right, we have all of Australia ready. We actually also have all of the US ready. I did ask my team to please add at least a few Indian cities. It was a bit trickier to find the elevation data, good elevation data, but still I asked them. So I can quickly show you how easy that is. Let's see. I think exactly. I got Chennai, Bangalore. I got, I think, Mumbai and Delhi, but let's now look at Bangalore. Someone wants to come in. Okay. So we basically have the big catchments around Bangalore. Now via the API, you just give it catchment IDs. We always think in riversheds and catchments, but you can basically just say, okay, maybe for this demo now, I want to use all of them. So that's 5,000 square kilometers. Apply. And then you can say what you want to run, right? So do you want to run a 3-hour event, 4, 5, 6 hours? For the sake of time, I'm going to leave it at 3. You can say I want to run a hyetograph and I want to run 100 millimeters. But if you say, hey, my climate scenario actually says it's going to be 120 or 130, okay, put it up, right? Put it to 130. You can really run whatever you want. Confirm, go. And now these jobs are being launched, and this thing is going to run in the next few minutes. And let's hope it works. I mean, usually when I give these demos, everything breaks down. You know how it is, right? But let's see. I mean, it's still early enough in Switzerland that I hope my engineers are not working on this. Let's give it a moment. But yeah, this now runs in the back, and you'll see the results in a minute. Again, here, of course, this is completely uncalibrated. I want to be very clear here. This is just rainfall and elevation data set and the land cover data set, assuming 100% salt saturation. So it's a very, very simplistic model. That then, of course, still needs the job of a good modeler to say, okay, what are realistic input parameters to make this a meaningful simulation? Sure. So here I ran a slightly smaller catchment that was as a test. Let me take the attachments away so you can actually see it. So yes, then you see, right, this is really full 2D hydrodynamics over the whole catchment. And then zoom in. You will see here a bit of artifacts because in the back it's actually a 30-meter DEM that then gets upsampled to a 10-meter. So it's not as nice as I would like to have it. No, I mean, so the background data is OpenStreetMap, so you see the 3D buildings, right? The DEM here, we're actually using FAP-DEM. Yeah, which I think is by now the best available global data set. We are working internally on our own elevation data set algorithms to clean SRTM, for example, and enrich it with LiDAR data sets, because we realize this is really now the big bottleneck, right? We have this with our client in Australia. We first used the 30-meter DEM in Australia, which is a hydrologically conditioned 30-meter DEM, which we thought is great, right? But it had some severe issues. So then whenever there was better data available, we basically automatically switched to the better data, and we're now working on an algorithm to produce that in-house. Yeah, so my engineer told me not to use the depth tool because then the UI will break. So I will not do that. In this case now, the dark blue is a max depth of 3 meters. and I think a minimum depth of 30 centimeters. Everything else we make transparent, simply to not have everything sort of in a light blue shade. But yeah, this can of course then be. I hope I didn't make a mistake now, and the UI is going to break. It's always great with this fairly new developments that stuff is not always working. I think. Oh, I might have broken it now. Oops. Yeah, this happens. It's still work in progress, but this was 3 meters max depth. Exactly. Yeah.
Okay, yeah, my question so is about the technical so details of your simulator. So what is the data set? And so what is the algorithm so you can deploy so for the of the emulator? Yeah, I just want to understand so the technical so perspective so of your model.
He's asking about what is the technical limit of the model.
Data set and so the algorithm.
Like how you did the AI modeling, so if you can go to the
How we did it. Okay. So sadly, there's not that much that I can tell you for two reasons. First of all, because I'm not allowed to, because this is intellectual property of the company, and secondly, because I don't know, because I'm not one of the technical team. That's why they sent me to speak. Because if you ask my chief science officer that question, he will tell you everything and give away all our secrets, which is why we tend to leave him to actually do work. But look, in the end, so I can tell you a few things. We tried in the beginning just producing, similar to HackROS, producing a simulation and using this so we're using convolutional neural networks, CNNs, right? Using outputs of simulations to train the CNN. This works, but it only works for that specific location. So that basically means we could have run the HackROS simulation for Bangalore and then train with this a CNN, a deep neural network for Bangalore. But then if you want to apply the same thing in Mumbai or in Beijing or in Zurich or in Atlanta, this would not work. It's not generalizable. And this for us is not a good solution because it defeats the purpose of saving costs, right? If you have to retrain and reproduce data for every new catchment, it really defeats the purpose, right? That means for India, you'd have to first generate training data for every Indian catchment. We don't have the money for that, quite frankly, or the time, right? So then we went to building our own numerical solver, not from scratch, it's based on OpenFOAM, but building our numerical solver and trying to figure out what kind of output data and which quantities do we need to have as an output and how do we need to train so we can make it generalizable. Because the other thing you might notice, so I just showed you the Texas example, which ran on 1,500 square kilometers. With HackROS or with other numerical solvers, it's very, very difficult to run a simulation over 1,000 square kilometer, 10-meter resolution. It's extremely expensive, and at some point even you hit memory limitation and it just doesn't really work. In other words, the model has never seen such a large catchment. So we also had to figure out how do we train on tiny areas and make the model then understand how to deal with large areas, right? So that was one of the key challenges we had to overcome. And I mean, in very short, you saw this before, we're dealing with these squares of training, right? So the model really thinks in these squares, small flow situations, and that's how it's generalizing across the whole catchment, right? So you can really almost think of it as a moving window that goes through the whole catchment with this square and basically moves the model forward minute by minute. That's maybe another interesting point of view. So the model thinks in 1 minute resolutions, right? So I mean now.
Yeah, so related to that so point, yeah, so if I was so the officer from the Bangalore the municipality so the government,
Yep.
I made so the want to so the train so the US models on the specific so the data. So
Mhm.
I mean so transfer the learning.
Yeah.
So yeah, now the this solution so is very nice. We can so the uh predict so this is the fast so the crash so the drug, yeah, everywhere. But
Yep.
so as the sort of government, we try to sort of detect equal accuracy.
Yep.
Yeah, now so that we need to sort of encourage so the citizens so to evacuate so from sort of cloud.
Mhm.
But the accuracy is matter. Accuracy matter. So yeah, so how can I sort of train so that this models on a specific so data set I have?
Yep. So we specifically try not to train on specific data sets to keep the model generalizable. But of course, you can then calibrate your model like you do with HEC-RAS, right? So you can calibrate Manning coefficients, surface roughness, surface friction, right? You can put your own land cover data set, your own elevation data set. We really try to separate what the model does, which is just fluid dynamics, from the input data set. So the calibration happens on the input data sets, right? So I would not want to develop a model specific for Bangalore. That would kind of defeat the purpose, right? But I want to give the Bangalore government, for example, the capability to calibrate the model with the input data. So they have full control over which inputs to put in, how to, calibrate those inputs so that the model outputs are as accurate as possible. Yeah, it's already finished a while ago. Yeah. Pretty, you can unmute yourself and ask your question. Not sure if you heard that. Oh, yeah.
Hi, sir. So I just want to ask, so have you considered, so in the numerical model and in the AI model, so have you considered the spatial variability of the rainfall? Because I have seen, so 100 over 6 hours or over 7 hours. So I just want to ask whether the spatial variability of rainfall has been considered or not.
Yep. So the question was whether the spatial distribution of the rainfall has been considered, because in the simulation I put in 100 or 130 over several hours. So in this specific simulation, the answer is no. It has been assumed that the rainfall falls homogeneously in space, but varying in time. So we basically apply a fairly simple heterograph that has its peak after the first third of the full event duration, and then it goes down again. The model itself can, of course, deal with fully spatio-temporally varying data. So you can put in rainfall events that move. I mean, that's what the demo you saw for Texas, for example. Or now, actually, we have a US and an Australian client that have their own weather data in the API. So what they do is they just go to our API. They say, I want this location between 1 a.m. and 10 a.m., for example, and it goes, gets the right rainfall data and runs an event, right? So really fully varying in space and in time.
David, I will just follow up with what UG asked that regarding the calibration. When you said that, the local agencies can do the calibration and you have an API. So my question is, does the API has a provision at all for calibration? Or it is you mean that you just upload more data and your results would be more accurate, which is not a calibration, by the way.
No, that's...
Yeah, so what do you exactly mean? Do you have a provision for the user to calibrate the model, or it is just you can fine-tune the model?
Yeah, so, and here, of course, we're talking about the flood model as a whole, right? Not about the AI model in itself that calculates how the flows go. But basically, this is a tool that's still used by flood modelers in the end, right? So this is not a tool for the end user that just blindly throws more data at it. It's a tool for people like you, really, right? That really know how to calibrate a flood model. So how to, change Manning coefficient, surface roughness, surface friction, how to maybe choose the right land cover data. And there's two separate things. So in terms of base data, changing the land cover data or the elevation data, you can just do basically as an input, right? Currently, the model points to this geotiff or net CDF. You can point it to a different one, and it works. When it comes to Manning coefficients and all that, it's a bit less straightforward. But basically, you can have a mapping table, right, and say this land cover class equals to that surface roughness, surface friction, and so on. So it's highly customizable. Right now, the API itself doesn't have that because our users are mostly weather companies that just want to put their rainfall in and get flood out. But I mean, you see, I can quickly show you this here. This is of all the areas that ran. In the back, actually, this is basically a Python module that you can access with, here you see a whole lot of data. So here, for example, you have the land cover data, you have the DEM data, you have a whole other range of duration and so on. So it's really fully calibratable in the back. But it needs an expert, right? Clearly, it still needs an expert to run this. No. No, this we don't do, right? The AI model in the end, that's very important, right? The AI model only tries to imitate what the shallow water solver that we trained it on does, and that's fixed, right? That does not change. Yeah.
Right.
Hey.
So I also work on flood modeling, basically. So all these maps are very similar to me. So I just wanted to know, like instead of in spatial variability, how you are considering time variability in your model. Like if you're running in the whole simulation, like if you're running it for like right now you ran for 120 mm 3 hours, 3 hours time period, and you ran for 220 mm rainfall. So like these maps that you have got, that is after how many hours of simulation is this map coming out?
Good question. So here the simulation duration was set to 3 hours. The map you're seeing now is the maximum depth over those 3 hours. So basically just for every pixel, it takes the maximum depth that it has seen. In theory, let's see, I think I probably have to, yeah, exactly, deactivate this. It also produces a time series. Let's see if this works now. You can tell I like risk by doing demos of stuff that has not been tested. But it's loading, it's coming, yeah, you see. So you also have the full time series of the event, right? So usually the model puts out 2 things. It can actually put out 3 things. So it can put out the maximum depth, which is not tied to a specific point in time, but really just every pixel shows the maximum depth over the whole event, which is very often what our clients want in the end. So for most warning applications or also for most insurance applications, they really just care about the maximum depth, which pains me a bit because I think actually the duration and the onset time and then the outflow time are extremely important. We talked about this briefly before, but insurers particularly are not yet really ready for this. And then you have the evolution over time. As said, the model itself thinks in 1 minute time steps, but usually we put out, I think this is now 15 minutes or 5-minute time steps. So you can vary this. I mean, if you run a 24-hour simulation, you don't want 1-minute time steps. It just gets huge files that are a bit hard to work with. And then, of course, the model can also do fluxes. Right? This we don't show here, but in the back, of course, the model thinks in fluxes. Right? So you can also see the flux. So you could, it's actually something I might want to ask my team to do, to show nice flow lines. Right? So you really see where the water is flowing to, which can be really important. For example, if you talk about risk resilience measures, right? How to design your resilience measures to understand where the water is actually coming from and where it's flowing to.
Just one more thing I need to. Suppose if you're running a model for 3 hours, that 120 mm rainfall is an instantaneous rainfall, or it is distributed about in those 3 hours?
It's distributed. In this case, we use a hyetograph. I mean, you can also steer the hyetograph parametrization if you want, but it mostly follows sort of I think it's mostly a gamma distribution almost. So basically after the first third of the time you have a peak, and then it slowly goes down, right? Of course, you can also say I want to run my rain for 3 hours, and then I run the simulation for 6 hours to see what happens in the 3 hours after rain. Things like that you can do. So this is fully customizable. Or as said, you can also put in a raster data set of rainfall rate that can be in 5-minute, 15-minute, 1-hour intervals, as however you want, right? So you can really also design your own storms completely. Asking the relevant question. Yes, short, yes. I mean, we're an extremely academic team. It's in a way, it's a bit funny that they sent the least academic person to talk in ISC. I think still the only person without a PhD in the team. But our chairman has 2 PhDs, so on average we still average out. But no, absolutely right. So we come from academia. So most of them are from ETH in Zurich, the technical university in Zurich. And yes, we're seeing how we can do that. I mean, basically for pure research purposes, we don't want to charge for this, right? I mean, it's obviously actually a very powerful tool to do very interesting things with. And I mean, I don't want to seem too nice and kind, right? This also helps us. Like if someone uses this and has academic publications with it, this is helpful for us as well to learn, but also as a business to advertise. So yes, we are planning to open this in limited ways to certain institutes. We also talked to Stanford, for example. Happy, of course, also to have discussions on that level if that's something that you're interested in here to use. That's definitely a possibility.
It's a wonderful presentation and a wonderful tool. I have two queries. How do you integrated the building data is my first query. And my second query is I'm more interested in validation. So how are you validating your model output?
Yep. So the question number one, no, we have not. I mean, you can see here it looks very nice, but you can also see it doesn't interact at all with buildings, right? It's just that 3D buildings are in there. The reason for that is very simple. Right now, the model thinks in 10 meters, and resolving building outlines properly in 10 meters is hard to impossible, so it doesn't make much sense. The next model version that the team is training is going to be a 5-meter model where we do want to put buildings in, and not really buildings with full, fluid-solid interactions, right? Which is of course, computationally extremely intense numerical models. For now, what we can see is that the AI model probably will run in exactly the same time as it does now. That's really going to be very interesting. And then on the validation question. So there's 2 steps to this validation. Step number 1 is to run the same model inputs, so the same model calibration in the numerical and in the AI model, right? And we consider the numerical model our ground truth. So we really want this AI to imitate the numerics as closely as possible. This is incredibly important because our clients also very often ask us about, well, can we trust this, right? Like numerics is very powerful because it feels that it's understood. In the details, there's always some questions there too, right? But basically numerics you understand, you can control, you know what it's doing. And with AI, there is always this black box character. And it is a black box, right? The deep neural network is to some degree a black box. So the best we can do there is to really say, hey, compared to the numerics, the results are stable and very close to what the numerics put out over a large variety of situations, right? And it's an ongoing, very, very intense discussion that we're having in the team about how we build our validation benchmark, right? Which data sets that we use, which simulations that we run, because of course some simulations are really edge cases, a lot of rain over very steep slopes, which the model is not very good at, for example, but then quite a lot of rain over regular terrain the model is good at. So that's the first validation, right? And just there we use this Nash-Sutcliffe efficiency to make sure that we have a good control of what the AI is doing. The second validation is with real world events, right? And that's usually what clients really ask for, is like, does this work in reality? And that's also the tricky bit when we sell to, for example, weather companies who are not flood modelers, right? Because they don't understand flood modeling. And then you have to first educate them and say, hey, reality is very complex, and the model can only see what the input data sees, nothing else. I mean, for example, in Australia, we had a case where the guy goes, hey, your model thinks there's 5 meters of flood depth in the middle of an urban area. Your model must be completely wrong. And then we looked at the DEM that we used, and indeed, the DEM had a 5-meter hole in the middle of an urban area for no good reason at all, right? So there's this kind of education that we have to do. But then, of course, and let me see if I think I might have here, if I can open this presentation. It's the same cases more or less, but I have a bit more validation in here. Let me go to the Australia case. You've seen this before, did you? Yes, you've seen this before, right? That's the Australia case. I'm going to jump over this. But of course, then it becomes very important to have data from these events from the ground. Now, as you're aware, there is sadly no good data set that gives us systematic event data over many events. There is satellite data. Fun fact, I happen to have a master's in remote sensing, and that's why I don't really trust most of the satellite data. It's nice, it's useful, but to really do validations with fluid dynamic simulations, it gets very tricky. They usually have holes in urban areas, in forested areas, even ICWaR, who we like a lot. So what it really comes down to quite often, sadly, is then really looking at what's happened on the ground and finding as many pictures and stories from the ground to somehow validate that the model has been performing well. It's very unsatisfying, I have to say. It really pains my heart that we have to do this, right? But it is so far really the best we can do to really make people believe that it works. Plus, of course, the gauge comparisons that you've seen, that's very helpful. However, gauge measures, of course, and that's a topic I don't want to go into too much, but in the US, for example, there's a lot of good river gauges, but also the rivers are heavily controlled with man-made structures, right? The model does not know man-made behavior, right? Of course, you can then model that if you know a specific operation protocol of a dam or whatever. But then usually have these kinds of issues, right? Where, yes, the model deviates from reality because humans were in the middle of it and somehow influenced proactively how things were flowing, right? But at least for the cases that we've run so far, we've been sometimes very impressed, sometimes fairly impressed with how the model has been performing. It really depends a bit on the event, on the city, on the infrastructure. Here in Brisbane, it worked really nicely. We also, maybe this might be interesting, we ran an event, there was a massive flood event in Thailand last November, which we only had really bad data for. So we didn't really get good weather data and we didn't have a good DEM. But nonetheless, the results were satisfactory, I would say. But the same topic there, right? We then have to look for proof on the ground. So I think here I have, let's see. It's coming. Yeah, exactly. So then here I have things like this, right? Where you have these very impressive pictures from, they tried to put their cars on the bridge because they thought they were safe. And well, a few lucky ones were safe, but whoever parked their car sort of on the side of the bridge was not so lucky. Trying to confirm this, right? But again, it's always individual observations, right? So I'm not aware of a way to really do proper real world validation on a large scale spatially, right? Because there's just no ground truth. It's so the clients we currently have are mostly weather companies, unsurprisingly. In the weather, so it's quite an interesting topic also in terms of AI. So in weather forecasting, there are a lot of companies that are active in the AI space, using AI to speed up weather forecasting. Side note here, it's quite interesting maybe for you. Weather forecasting is, I would call it easier from a technical point of view. It's very expensive, but it's easier in the sense that weather data exists as a closed system, which can be used in full to train an AI model. So you have a closed system you can train on. With flooding, we don't have that, right? Because we cannot, with HEC-RAS, simulate 3,000–4,000 square kilometers and use that as a closed system ground truth. So we need to have something as sort of an open system. So technically, it's much harder. But to go back to the business question, so we see a lot of weather companies, but they all produce weather. And they're struggling because they say, hey, my weather forecast is much better than the public weather forecast. But the clients say, well, so what, right? I can't really prove that it's now 110 millimeters, but the forecast was 100 and the public one said 90. If I stand outside, I have no sense if now 80 millimeters was correct or 100 or 120. It's very difficult for clients to really say that it's worth paying money for a commercial weather forecast versus the public one. But no weather company has flood forecasts, and no weather company has flood forecasts that cover an entire continent, right? And that's our easiest way in because they're fighting for market share, right? And most of those weather companies are then selling to governments, of course, but they're also in Australia and in the US. Usually one of the biggest segments are railroads, because you have these massive cargo railroads that transport tons and tons of very expensive either coal or iron ore or something across the continent. And from time to time, there's a flash flood that just makes the train bed uneven. train derails and you have a 30, $40 million loss, right? So these are very, very keen to have high resolution, even short notice flash flood forecast. Because even if you send them a forecast 20, 30 minutes before it happens and just say, stop your train, that might save them 30, $40 million, right? We are working or trying to work with governmental entities. Usually that's more project-based. And as you can imagine, much slower because there's, well, politics involved and governmental processes. So we're usually looking at actually working with other institutes that work with governments because it's just much easier, particularly if you're outside of Switzerland. I mean, we would not go to the Indian government and contract directly, for example. That makes no sense, right? When there's other institutions here that have already good connections and do projects. It does make sense sometimes, yeah. But for us, I mean, we're currently a very small team. Yeah, so we're very happy to collaborate. Sure.
Maybe I missed. What is the smallest square that you do?
The smallest resolution, yes. So the current model works on fixed 10 meters. So 10 meters is the smallest resolution we can currently do. The next model iteration will come in 5 meters. So we're working our way towards a 5-meter model. We are currently debating if we want to go further than that. Theoretically, there's, of course, very good applications with LiDAR data sets. We have super high resolution data sets that you could run on 1 meter, even half a meter. But the question is then, do we really generate more insight for our clients? That's an open topic. Depending on the application, the answer is yes or no, right?
Follow-up is, can you also do the same like you have shown for urban areas? Can you do it for forested or rural areas?
Yeah, anywhere. So we really, I mean, the model basically has a link between land cover and, as an input data, link between land cover and surface roughness, surface friction. So yes, it works anywhere. You can also steer this. In fact, we have a project that's now rolling on in Ghana, where there's like a 25-year project for reforestation. And one of their main questions was, well, we're going to have good flood data for Ghana, and we would like to know not just what's the current flood risk, but also if we plant a lot of trees, do we increase resilience of villages nearby because we change their susceptibility to flooding, right? This you can very easily do, yeah.
Follow up from a business point of view. Have you approached city planners or property developers? Because this really fits into how we can plan the infrastructure.
Yeah, so funnily enough, so far, no, we have not. For a very specific reason, at least that's what we see in Switzerland. If you look at particularly on engineering companies that do really specific building projects, they want numerical models because they trust numerical models. And as much as I love my product, of course, but you saw it, it's 80% Nash-Sutcliffe efficiency. There is a risk involved there if you want to really, really, really accurate results for a specific building, right? Usually also that comes with certification, right? Certain ISO certificates that you need to do this kind of consulting. So we're a bit hesitant yet to go into this because we think the power right now is in the large scale applications. So city planners, yes, potentially, because you can really do full cities, right? But once you go into specific projects, I would still recommend going with a numerical model, right? Because it is AI, so it is assuming things. It's still a statistical model in the end.
Any last question?
Hey. Well, in practical terms, it is learning from the physics equations, right? But if you want to use a convolutional neural network, it will always stay a black box in some sense, right? Because in the end, the way these models work is that whatever they're trained on, they will transform it into matrices, and then there's just a bunch of matrix multiplications that give you the result. So I think in effect, it's always going to remain a black box. So the best we can do is really to say, hey, if you compare it to numerical results, it is stable. Yeah. Yeah, for those online, the question was whether we also enforce soft or hard physical constraints. Yes, in a way, yes. During the training, this happens, and that's what even enabled us to do this in the first place, right? If you just throw flood data at it, the model will never become stable. So there are certain constraints that are imposed, mass conservation, momentum conservation, practically, right, to make sure that the model remains meaningful. But yeah, I mean, still in the end, you have this black box element because it is a DNN, it's a deep neural network.
Just want to make my in the US, the Federal Emergency Management Agency came up, said that in your area, the waffle house, which is a popular food thing, the waffle house is open.
You're safe. You're safe.
First remark. The second remark, I think for Bangalore also, we try to get this kind of photograph from the local residents. Also, time to time, we try to access the Bangalore traffic police data because they have set up the traffic cameras in the junction. But that is always difficult to get. The third thing, I remember one of my students, he tried to take out the Twitter because from the Twitter they can do the geolocation and see that whether really those areas. So thank you so much. I remember you wanted an engaging discussion.
I got my engaging discussion. Thank you. Very good questions. Likewise, thank you so much for your attention, and yeah, have a good day. Thank you.